Greetings. This is a video detailing the process behind completion of our first lab project for the course EEDG 6370 at the University of Texas at Dallas. My name is Ojas Kasbekar and I shall be sharing the process of this project along with my partner Varun Kuchibotla. The project involves the design of a 1-bit full adder using both schematic entry and Verilog VHDL on Quartus Prime Lite by Intel. The first thing we did was design the schematic entry and we used this to create an RTL sketch. Once the RTL sketch was created, we created a test bench and added both the files to this project while deleting the schematic entry itself. After we finish this, we run the simulation. Now, as we can see, our simulation is complete and we have found no errors. We then proceed to look at the filter, which shows us the amount of hardware resources allocated for this particular circuit. As you can see here, we use two adaptive logic modules, ALMs in design, and three ALUTs, adaptive lookup tables. Since this is a fairly straightforward design, there is no need for specific flip-flops, lock ramps, or any specialized DSP blocks. Now we check if our design is functional. We click on Tools, go to RTL Simulation, and this opens Questa. We compile the relevant test bench, simulate it, and observe the waveforms. As you can see, we have simulated it for 1000 picoseconds or 1 nanosecond. Once we begin our simulation, we see that this is the result that's obtained. So the test vectors used basically correspond to the truth table of a 1-bit full adder. That is, all the possible inputs of A, B, and carry in, as well as the outputs, which are sum and carry out. This result is concordant with the expected results for a 1-bit full adder. We shall now examine the critical path of the circuit. We go to the timing analyzer, go to tasks, and then click on report paths. We then give our inputs and outputs in the form of field, two field respectively, two fields respectively. We then analyze the critical paths. We see here that the delay is in nanoseconds. Now that we have completed simulating our 1-bit full adder and ascertaining its critical path, we repeat the process again using our RTL code that was written by us. We created our RTL module, whereas the schematic entry had an RTL code generated by the software which we used to complete the simulation. We created its relevant test bench, which was fairly like our test bench for the full adder. We shall run compilation. Once our compilation is done with no errors, we once again consult the filter, which will give us the information on the resources used for this particular circuit. Now, as you can see, we have gotten 0 errors. Now we see here that the logic utilization is pretty much identical when it comes to the logic module. As you can see, yeah, and all our LUTs are also pretty much the same here. Now we shall proceed to simulate the design. And as you can see from these waveforms, both the results are pretty much identical, showing that we are able to successfully design a 1-bit adder using both schematic entry and conventional RTL. As you can see, we once again ran this for 1000 picoseconds. So now we shall proceed to as we can see, both the results are pretty much identical, showing that we are able to successfully design a 1-bit full adder using both schematic entry and conventional RTL. Now we shall analyze the critical path for these circuits and compare the two. RTL code critical path. As you can see now, from this comparison, we can see that the delay is much greater on the RTL than it is for the schematic entry, showing that the software does a good job of actually optimizing the design. This concludes the first part of our homework. Now, the next part of our assignment involves is the design of a 4-bit full adder using both structural as well as behavioral Verilog and comparing the resource use as well as the critical paths for the both. So as you can see, this is our structural Verilog file that is in use. It contains an instantiation of 4-bit adder module along with 4 instances of the 1-bit full adder created before. So as you can see, there are 4 1-bit full adders which constitute 4-bit full adder. Having created the test bench, we shall compile it. Now as you can see, the compilation is finished. So we shall proceed to simulate our design to check its functionality. As we can see, we have a successful simulation here. Now that we have finished checking and that our design is functional, we will now proceed to look at fitter. We see here that the logic utilization involves 4 ALMs, as you can see, and we have 7 ALUTs here. This is structural Verilog. So we will keep these distinctions in mind when we are compiling our behavioral Verilog design. As always, there are no DSP blocks, nor is there specialized block RAM. We shall now proceed to analyze the critical paths of this design. The delay is in nanoseconds. So the delay of this critical path is 7.765 nanoseconds. We shall repeat these steps for behavioral Verilog and compare the results. Once our compilation is done, we should proceed to look at the fitter. Now you should see the number of ALMs used. In the resource section, you can see that the number of ALMs used is 3 and the LUT's logic is 6. Now let's compare it to our structural. So now here, when compared to our structural Verilog, we see that it uses 4 ALMs and 7 ALUTs. So our behavioral Verilog actually reduces our resource usage. However, when we take a look at the timing, we see that in fact it has more delay and the critical path has changed. Now this could be because, as you can see here, the number of parts taken by this particular design is a couple extra compared to the full adder. Compiled with structural Verilog. So what we can infer from this is that software itself is able to reduce our logic requirements. It is still increasing delay for through other means by way of adding extra more intensive cells along the way. This concludes our first homework. We shall see you next time.